Okay, if people could take their seats, we're going to start this session. This is sort of in keeping with AGU's efforts to try and bring science more into the eye of the public and have an understanding of how our science fits into shaping policy. And this session is called Living on the Edge, Societies on the Front Line of Coastal Change, which, given the recent events in the Northeast, is obviously pretty topical. We've tried to get a range of talks from people that cover the stakeholder base through to some basic science as well. And the first talk in the session is given by Susie Moser, who works for the Union of Concerned Scientists, and her talk is titled Restoring Land, Restoring People.
Hello, everyone. I haven't worked for the Union of Concerned Scientists in about 8 years or so, so I'll just correct that, but be that as it may, doesn't matter. I'm going to start this with a truly social science talk on how folks in southern Louisiana are living with the coastal change. Anyone here has seen this movie? I can't barely see you, but I hope there are a few of you, and if you haven't, you should see this movie. It's a fabulous movie for a whole number of reasons, including the fact that it depicts a number of people living on the southern fringes of Louisiana and struggling with the impacts of hurricanes and land subsidence and sea level rise. And of course, dutifully, as you would expect, it says there, this is entirely fictional, no resemblance to any characters alive or dead should be assumed, except for the fact that it is not entirely fictional. This is, in fact, what people there are living with. These are real pictures of real places in southern Louisiana, and the state has fully recognized that problem. And many of you may be familiar with this. If not, this is a remarkable document that I would also recommend for you to ingest, and that is a master plan for how to deal with the land loss, flooding risks, and the need for restoration, protection of certain areas of the land in that region. Now, what I want to tell you about is the human side of that. What you see here is just how they have recognized the flooding risks and the land loss under different scenarios of sea level rise and subsidence. By the way, the word climate change is not mentioned a single time in this document. It is remarkable, however, what you can say about the impacts of sea level rise without ever mentioning the word climate change. What I would say is remarkable about this document is about the courage to actually recognize loss. This is not something that you hear often. You certainly didn't hear it much before Sandy, even after the Hurricane Katrina. This was not something that was mentioned very much. Here they actually say, we will be able to protect some things, restore a few other things, and we will lose yet more. We will lose a certain amount of land, ecosystems, and the places where people live. Now, how do you deal with that? There's a huge part of this document that is all about, the technical construction of protection and restoration, but there is an aspect that is also funded to deal what they call with non-structural programs with people living in that area. Let me just quickly say why this is an important human story. What you see here, this comes from a different study, Martinich et al. Published this a year ago, which looks at the social vulnerability of communities around the country. This is just an excerpt for the map of the coast in the Gulf, and the darker pinks that you see are people who have very low adaptive capacity to actually afford the kinds of things that you would do if you could build a protective structure around you, if you could restore the land. If you are in a very pink part of this map, you're most likely to not be able to keep your land from and protected from sea level rise. This is a graphic that they publish along with it, which basically shows on the left the lower the. Can I just quickly look at this? It's hard to see. Basically, the richer you are, the greater your capacity to protect yourself. The poorer you are, the likely you are to need to retreat. and most likely an unmanaged retreat from the coastline. So what you saw here, quite a bit pink in southern Louisiana. And so the central focus of this document, I think, is right on the front cover. It is the people. How do we deal with people who will lose their land, or people who will lose the access to the ocean resources that they depend on for a livelihood? Here's the set about the non-structural projects that they have in mind that they want to do: land use planning, upgrades to building codes, implementation of ordinances, public education. I mean, it's nothing, spectacular at all in here. But, a few sort of technical measures to support that effort. And what they're saying is we also need to talk to our people. And so my interest here is in how do you engage with people when loss is assured, when they will have to leave a certain amount of area of land. What they have done in the preparation of the master plan is shown here. For many of us, this would be a phenomenal approach if you had thought about it this carefully, with looking at all the different elements of integrating them: planning, research, program management, the policy and legal side, with that outreach and engagement. And in fact, they show you here how wonderful their engagement was. They checked all the boxes, if you will, in typical outreach approaches practiced in coastal areas all over the country. They have held meetings, they have had hearings, they have informed people. And here is now some, coming out of that, then what else they want to do. Needs assessment, staff trainings, more education, supporting local capacity to amend regulatory approaches. And as someone recently stated, the Coalition for the Restoration of Coastal Louisiana, it's just not enough to do that. People are highly resistant to this form of being informed about what's going to happen to them. Imagine, put yourself in that place for a moment. You are in a house that is not going to be protected, and all you get is you're going to be informed about it. Like, how likely is that to satisfy you? Well, it doesn't satisfy folks in southern Louisiana either. So, how do you start? I think the first place to start is to acknowledge loss and change. And you have to do that in the context of what in psychology is known as place identity and place attachment. People in southern Louisiana are deeply connected to their land. Their whole livelihoods, their cultures, everything is interwoven with that land. This is just a list here of all the dimensions that that term, place attachment and place identity, has. Who they are is deeply interwoven with the land that is now going under. The first thing is, and this is maybe the hardest thing, is to face that truth. That is a difficult conversation to have. You don't just send that in a Federal Register notice or in a, in a newspaper one way of conversation. This is something that happens best in interpersonal conversation, in group conversation. And then you have to figure out, how do you deal with people who are grieving over what they lose? This is something that we barely ever recognize in this country, that actually, when you have loss, you have to also grieve. We don't make room for that, certainly not in public hearings. To help people move from that place to something else, to a different future, to a different home, to a different piece of land, a different kind of livelihood, you have to frame that transition or that move as a transition with all its ups and downs of, whether you want to see that through the lens of grief and the stages of resistance to that or whatever, it doesn't matter, but there's a whole set of typical responses that go with it. We have to help people who do the outreach understand what that process is like psychologically. And then to be with those people in distress. I have, just in my own work of doing outreach on climate change, encountered it many, many times, that I was sort of the messenger with the bad news, and I've been dumped on, and I have, experienced the anger and the comments or the responses to that from folks. So this is a very challenging thing to start that conversation and to equip people to handle that type of situation. Now, what is the state actually doing in that? The most remarkable thing is that there appears to be a recognition in southern Louisiana that all this outreach that they've done before for the master plan isn't enough, and that they're open to experiment with different approaches of how do you reach consensus, how do you bring people into this conversation and empower them to take charge of their lives. And so here are just a few examples that are currently being discussed. There's, already there were first attempts to doing that. One of them in particular engaged some outsiders from the region and went completely flat. It was an insult to people. So it's going to be very difficult to pick the right messengers, to pick the right people to lead such efforts. I wish I already had more empirical responses for you. This is, I think, going to build very slowly. But it will be supported through, different and carefully evaluated how these different approaches work. Let me also maybe say a few words before I'm off the stage here about if you do lose, if that is assured, then what would success of such engagement and success for these people look like? Well, one of the interesting questions about this, I actually do some work on this question, not in Louisiana but elsewhere, about there's actually not very much evidence of what people would view as success if they're confronted with change or loss. But there are some indications, and probably you can relate to all of these. The first one is that when you ask people, what do you really want from the future, most of them will tell you they want something better than what they have. Now, that's a difficult proposition if, you will lose your piece of land that you live on right now. The next thing that they want is they want to at least keep what they have. And it sort of reflects the risk aversion or all of our own unwillingness to consider losses and change. And then the last one is that if I have to change, at least I want livable conditions. I want good conditions somehow. I don't want it to go below a certain minimum standard, whatever that very, personally or culturally and regionally is defined as. But we don't know very much what folks in this region would consider. There's no empirical studies that show what they would consider as loss, as a success in their situation. When you look at the master plan, the only things that they have indicated as measures of success of their engagement is that they have done a lot of it. That's the scope, that they have done it at the right time, that they've given everyone a fair hearing, and that they've made their materials and their information accessible to people. So they're all really about the process. It's not about whether at the end of this engagement you feel okay with the outcome. So to me, the suggestion here is that we need to also develop some engagement measures of outcome. And here are just some of them. All of them could be measured by social data that you could collect. People are able to recreate their lives in the new places. There is, even if they have to leave, that they leave together as a group and have a group cohesion. That there is continued or renewed connection to the land, so that they at least are able to retain that aspect of it. They continue to have productive livelihoods, they're civically or politically engaged, and that they feel good and are well in terms of health. Now, these are all, whatever measures we might come up with in the social sciences for that, they're not perfect, but tell me one physical indicator, one ecological indicator that's perfect for, say, biodiversity or whatever. They're all partial, and yet that could be at least an indication of it. Whoops, sorry, wrong direction. In my mind, one of the qualitative ways in which you would be able to tell whether it's successful is if you listen to people's stories, because their stories right now are very deeply connected to the land. Their culture is connected to the land. So listen to their songs, listen to their festivals, to the stories they tell each other, the stories they tell in church or whatever, and you probably will find out how well it's come out. And with that, I'll take a couple of questions and leave it with that. It's hard to see.
So we can't see anything up there, so if you have
Shout.
a question, please go ahead.
You said that for the engagement process that the state originally brought in some outside folks and that didn't work out so well. So are they now training local facilitators that they already have trust in the community on how to communicate on these issues, or how are they dealing with them?
Well, let me just correct it so I'm not conveying something wrong. When the state did its outreach, it was state employees who were involved in this planning process to do their outreach, the stuff that they did in the process of planning the master plan. But they have recognized that they've gotten a lot of feedback from people that this is not enough, and so from that, basically a project has sprung up that's led by the Coalition for the Restoration of Coastal Louisiana, and they suggested these different models that I listed there, and brought in an outsider, and at least with one of the projects I know, it was a complete bust. So that doesn't mean it couldn't be done again with a different group or something like that, but I think they're learning already very early important lessons of how to approach folks, and it typically implies you begin with working with locals in those communities that are affected by the lack of protection or restoration, so that it's an insider and not perceived as someone coming from far away who doesn't know anything about the place.
Sure, yeah, one more.
Well, I mean, the basis for their outreach planning and for their engagement with communities has to do with the maps that they produced, where they drew the lines of this is the part that we will protect, this is the part we will restore, and this is part that we basically are writing off. So in that sense, there are sort of priority areas for the state as to which ones will be restored or surrounded by a dike or whatever, and which ones will be let go. And so in that way, there's great certainty about the potential loss or not. Of course, that doesn't take into account, say, future Katrinas or something like that, and what that else might do to those areas. But certainly in terms of, where the state has said, here's where we're going to work, in that sense, it's clear. The scientific elements of it, I think, will be very much part, at least in some of the outreach approaches, the science will be a very strong part in the education of the people involved. But I haven't heard that that's the major focus of those outreach aspects. Okay.
Okay. Thank you. We'll move on to the next speaker, Christine Shepard, and she'll be speaking about building coastal resilience to sea level rise and storm hazards.
Hi there. Thank you for attending this session today, and thank you for inviting me to speak. My name is Chris Shepard. I'm a scientist with the Nature Conservancy's Global Marine Team, and I spend most of my time working within our Coastal Resilience Program, which is one of the core components of our climate and disaster risk reduction global strategies. And the strategy seeks to align our conservation efforts with disaster risk reduction objectives to do work in places that can help meet these objectives simultaneously. And the Nature Conservancy's interest in the role of natural habitats and systems in risk reduction really started about 7 years ago, and since then I've spent quite a bit of time in the science on the ecosystem services related to risk reduction that are provided by coastal habitats. And the impetus for this work was primarily two events, Hurricane Katrina and the Indian Ocean tsunami. And typically, many folks and many coastal communities think of these as acute events, but they're really symptomatic of a chronic problem. So this graphic here shows the significant increase we've been seeing in reported natural disasters worldwide. This doesn't come as a surprise to most, but what a lot of coastal communities don't consider is that although these are natural disasters, they're not an entirely natural event. Human behavior plays a large role in this. It's an interaction between the biophysical environment, human systems, and the built environment, decisions that we make. So human activities are really contributing to this trend that we're seeing an increase in reported natural disasters. And this is because we're developing in risky areas, and also frequently when we develop in these risky areas, we are destroying some of the habitats that provide some of these risk reduction benefits, and in doing so, increasing our risk further. So as I said in the introduction here, coastal habitats do play a role in risk reduction. And when I say coastal habitats, I'm describing mangroves, coral reefs, oyster reefs, and salt marshes. These are the four systems that we spend most of our time evaluating the role that they play in coastal protection and risk reduction, and how we can align our conservation and restoration efforts with these habitats with some risk reduction objectives. So as part of our coastal resilience program, we've developed a coastal resilience approach. It's pretty basic. There's 4 steps: assess risk, identify your solutions, take actions, and measure effectiveness. For today, I'm just going to focus on the assess risk and the identify solutions portion of our approach. And as you can see here on the slide, you can see the waves breaking on this coral reef here on the top. Similarly, you can see waves breaking on these hard engineered structures. So this is a comparison that's visually compelling, and one we frequently bring to communities that we're engaging with, because many times people don't realize that these same coastal habitats do play a role in the wave energy that's reaching the coast. And if you think about it, it makes sense. Many people vacation in Hawaii, and the place they want to take their children or the place they want to go snorkeling where the conditions are calm are usually affronted by a barrier reef. So it's something that makes sense, but only over the past 5 to 7 years have we really started incorporating this thinking into our planning. So the main tool that we've developed to start our outreach efforts related to the role of natural habitats and risk reduction is our Coastal Resilience Decision Support Tool. We developed this tool initially in New England on the southern shores of Long Island, and expanded it into Long Island Sound and the shores of Connecticut. And now we have coastal resilience tools developed for a variety of other geographies across the world, including the Eastern Caribbean, the Florida Keys, the Gulf of Mexico, Southern California, and the Mesoamerican Reef. And we're expanding our work on this tool and our outreach efforts surrounding it every year. And essentially, it's just an interactive web mapper. Most of us have been on these before. It includes information about socioeconomic vulnerabilities, ecological vulnerabilities, and hazards and sea level rise information. So the tool allows you to compare a variety of storm surge scenarios, sea level rise scenarios, and a combination thereof. So it really allows some of the local decision makers and municipal planners to visually compare some of their assets in relation to this risk from storm surge and sea level rise in a way that they likely didn't have access to this information before. And the TNC folks in this area have engaged with about 20 municipalities using this tool so far. As Susie mentioned, social vulnerability plays a huge part in all of this. So this is a map of census block groups with high levels of poverty. And this is one factor that goes into social vulnerability. And we also have mapped, in addition to this component, several other components in the social vulnerability index. These are census block groups, areas of people that, due to their socioeconomic status, they're more likely to suffer harm and be more vulnerable to natural disasters, people who don't have the resources to necessarily plan or get out of the way as much as some of us do have. So we have considered this as well when we developed the tool. There's also economic vulnerability information, property values, and also we have some damage estimates from a variety of storm surge scenarios and sea level rise scenarios, so estimated economic losses. We have critical facilities information as well, and oftentimes when we're engaging with the planners, we'll also engage with the emergency managers and the emergency preparedness folks to help them understand how their assets are at risk as well. We have information about coastal habitats both now and in the future. At many sites we've incorporated results from SLAM models, sea level affecting marshes, and what we're trying to do here is show folks this is where your habitats play a role currently. This is where we feel, that the models are showing that the marshes will migrate in the future, and you need to consider development decisions that might put impediments in the way of those marshes migrating. So I'm going to walk you through briefly kind of one of the examples of the ways in which we've used this tool to engage with planners. So on the left here, you can see we have a storm surge scenario, and on the right we have social vulnerability. So the circles are drawn around areas that are at high social vulnerability and high risk. In those same areas, you can look to see which marshes are found within those areas, and also on the right here you can see some of the results of our marsh modeling work, in which you can show these are the areas where the marshes are likely to migrate. Are they currently developed, these areas, or are they undeveloped? And if they're undeveloped, these are areas that should be really considered more thoroughly if there's development permits that are put in for these areas, because they're likely to be areas that are important in the future for these marshes to migrate. And you're going to have a further increase in risk if you allow these areas to be developed, and then as sea level rises, the marshes have nowhere to go. After Superstorm Sandy, quite a few folks were using the tool. We brought in some information on the reported surge heights into the tool, and we developed this little Marsh Explorer. It's a little tool that it's very basic. You can adjust different parameters, and then it'll prioritize the marshes based on those parameters. And how we're using this tool is just to engage with decision makers. The post-Sandy Commission is using this tool. They're going to be looking at the tool to say, okay, if we want to show we want to see which marshes are adjacent to large amounts of infrastructure or large amounts of populations, you can adjust the little slider bar, and it'll change which marshes most meet those criteria that the user has set for themselves. So here you can see it changes as you adjust each of the settings. So it's something that is just a visual exploration tool, something we can use to communicate the message that these marshes do play a role for a variety of different reasons, and allow decision makers to adjust the settings to evaluate those criteria that are important to them. We also have work going on in the Gulf of Mexico. I'm traveling to Galveston Bay tomorrow to work with some local folks on starting to engage with communities on where they can use living shorelines, artificial oyster reefs as natural breakwaters. So we've been doing a lot of work with the Natural Capital Project, a partnership of TNC and Stanford, to look and see, where do habitats play a role in risk reduction across the Gulf of Mexico, and specifically in Galveston Bay and Charlotte Harbor, Florida. And we've also developed a tool which we're going to be training some municipal planners on, where they can actually go into the web mapper and click on a point, and we've worked with some coastal engineers to put the parameters in for breakwaters, and the user can propose an oyster reef, and then the system returns a value of wave attenuation based on the wave climate in that area and the parameters that they've put in for their proposed oyster reef. So we've had quite a bit of success in Alabama with them using this tool to propose and then put actually in the water oyster reefs that serve as breakwaters. And finally, we have quite a large project in the Grenadines and St. Vincent and Grenada. And this project is really stepping up the science about the ecological vulnerability of these systems, and how the social vulnerability and the ecological vulnerability are related, and how these natural systems really mediate the social vulnerability. And they've developed quite a bit of science looking at the ecological vulnerability of mangroves in particular, and we're working on a publication right now, and we've looked at the adaptive capacity of mangroves, how and where they're able to migrate, the exposure to hazards in sea level rise, and the sensitivity of these systems. So in summary, the Coastal Resilience Tool, it really doesn't give the answer, but it's an excellent outreach tool that we've used to kind of share the socioeconomic and ecological vulnerabilities, and really starts a discussion about these things with these communities. It's very effective for outreach with the decision makers and the planners, but also the citizens in Florida, and Punta Gorda, which is in Charlotte Harbor in Southwest Florida, we have a workshop planned where the first half of the day is with citizens who want to come in, and we're developing a tool there to help them identify which areas should retain natural habitats because they're important for hazard mitigation, and sea level rise, which is something they are willing to talk about there, which is was a little surprising to me, but they suffered from Hurricane Charlie in 2004, and they understand the role that their mangrove systems played there. And finally, the data and analyses and the modules and tools that we develop as part of the Coastal Resilience Decision Support Tool are constantly in development and can be tailored to communities' needs. So we show up and we have some basic information to start the conversation, and then we really look to populate the database and development tools that really support an ongoing or starting up decision process within these communities. And it's been pretty effective for us so far. So thank you.
Okay, we have time for some questions. Susan?
I have a question in terms of the effectiveness of the outreach. Can you say a little bit about what happened in response, other than just, you know, getting maybe the ooh effect, whatever, but what actually happens in response to you using this tool in communities?
Sure. So when we've engaged with some municipalities, we've gotten them to consider land acquisition as a flood mitigation strategy when they didn't previously have that as one of the strategies in maybe their hazard mitigation plan or their comprehensive plan. Through the efforts and the outreach with the tool in the New England area, the Nature Conservancy folks in the area were able to be a part of some regional transportation planning processes to kind of speak to the role of using the tool to evaluate sea level rise and storm surge impacts for transportation planning. And, you know, really they're influencing some decisions on the local and the regional level, and then regular folks actually were using, and even some municipalities, when Irene came through the area, were using the tool to get an idea of where Irene could potentially go and what the levels of flooding could be in their community. So initially we developed this tool to really inform some of our work and some partnerships with communities, but we found that over time, in particular after the Superstorm Sandy, I actually helped my mother-in-law look up what the storm surge height was on her childhood street in New Jersey. So, you know, it gets used in a variety of ways. Thank you.
Time for one more question.
Thanks.
Thank you.
All right. Our next speaker will be, I'm sorry, Hillary Stockton, and she's going to talk about National Assessment of Storm-Induced Coastal Erosion Hazards.
Thank you. Thanks. Holy mackerel, it is bright up here. Okay. So the image here on the screen is something we're familiar with seeing recently. Waves attacking a beach, causing erosion, maybe making houses collapse. But this picture isn't from Superstorm Sandy. This is from 2009, when Hurricane Ida's remnants moved offshore of Georgia, mixed with a nor'easter, and then delivered surge and waves to the coast of North Carolina as Nor-Ida. In the last decade, we've seen images like this quite frequently, from 2003 Hurricane Isabel, which made landfall in this same area, causing extensive erosion, and then in the Gulf Coast with Hurricanes Ivan, Katrina, and Ike. So clearly there is a need to be able to forecast how beaches are going to respond to future storms and able to identify areas that are more vulnerable to these extreme coastal changes. The model or methodology that I'm going to show you today is part of a larger effort by the U.S. Geological Survey in identifying coastal change hazards around the country. And this is from over a decade of work looking at multiple scales, temporal and spatial scales of coastal change hazards. For example, in the top left, those are about 100 or 150 years of shoreline retreat in North Carolina. At the top right is cliff failure during the 1997-98 El Nino storms. And then in the bottom, it's the event scale of extreme storms and hurricanes making landfall. And this is the topic that I'll be talking about today. Ultimately, the goal has been to quantify coastal change, model the processes that's making it all happen, and then be able to predict how our coast will respond to future storms. As an example of the types of coastal change I will talk about today, I'll use this example from Hurricane Isabel, which made landfall near Hatteras, North Carolina. Over this 5-kilometer stretch of coastline, you see 3 very different responses. First is dune erosion, which is simply where waves are attacking the base of the dune, causing extensive erosion of the beach and dune. Where waves get higher, the dune is lower, you see overwash or the landward transport of sand. And then in the most extreme cases where surge or the mean water levels are higher than the elevations of the beach and island, and you may see breaching. In short, what we want to do is, if you know something about a storm that's coming ashore and you know something about the beach where it's going to make landfall, we want to predict what type of morphologic response you'll see. And we'll do this through looking at the probability or the likelihood of change, the likelihood that the elevations of hurricane-induced water levels, which are surge and wave components, that will exceed elevation thresholds on the beach. First, for the collision mode, this is the probability that the highest waves in surge will exceed the base of the dune, leading to erosion of the dune face. We also want to understand the probability of these extreme water levels overtopping the highest elevation on the beach and pushing sand inland, and also the probability of mean water levels, which is surge and a small wave component, exceeding the highest elevation of the beach. We do this in a real-time mode as storms are making landfall with the oceanography for that particular storm. But also for planning purposes, it's important to be able to do this for generalized storm conditions. The first piece of information that we need is a measure of the morphology, or the shape of the beach for the entire coastline. And with the advent of LIDAR, or airborne laser surveys of beach elevation, this isn't as challenging as you think. This figure here is showing the elevation of the dune height around the Gulf of Mexico, measured every 20 meters. The blue colors are the lower elevations, and the red colors are higher. And you can see the spatial variability around the Gulf of Mexico. Over in South Texas, South Padre Island are the higher dunes, and then in Louisiana, Mississippi, you see very low elevations. The next piece of the puzzle is the water levels, and surge is obtained from NOAA's slosh model, and we're going to use the MOMS, which are a max of the max, so the highest surge that occurs for an ensemble of hurricane conditions. This is going to represent a worst-case scenario. The color bands here are showing the elevations of modeled storm surge for Category 1 through 5 hurricane. 1 is closest to the shoreline, and those are the blues, the lower surge elevations. You can see surge gets higher as you move to the higher categories. You also can see here some differences in surge along shore due to the shape of the basin. For example, the higher elevations near the Bird's Foot of Louisiana, where surge water levels are allowed to pile up. Equally as important as surge are the waves. For lower category storms, waves can increase water levels on the shoreline more than surge, in fact. What we've done is created a similar measure of waves as surge, a max of the max, a worst case scenario, by modeling the wave conditions that would occur for the maximum wind conditions for each hurricane, letting that wind blow in a variety of directions, and then taking the maximum value at the 20-meter isobath. It's this wave height that's going to be used in a model or parameterization for wave run-up, which ultimately delivers the wave energy to the coastline that's eroding the beaches. Put all the pieces together, and we are able to show the probabilities of a variety of coastal responses. The figure here is for a Category 1 hurricane, and the 3 bands represent the 3 types of coastal change. The inner band is dune erosion, the middle band is overwash, and outer band is inundation. The colors represent the probability, so pinks are low probability, red is very high probability. With a scale like this, you can't see much of the detail, but you see it's red, and red is bad, and we know this. The Gulf Coast is very vulnerable to extreme coastal erosion during hurricanes. But you can see some areas where there is some spatial variability, particularly in regard to overwash and inundation. And for example, the south coast of Texas, their higher dunes there made them less vulnerable. The west coast of Florida, the dunes are so low that this entire stretch of coast is very likely to experience overwash in even a Category 1 storm. Here's the same picture, but this time for the southeast Atlantic coast. These are the probabilities of the likely storm response measured every kilometer along the coastline. Again, a lot of red, meaning that these areas are very likely to experience dune erosion during the storms, a Category 1 hurricane. Then you can see more spatial variability along the coast related to overwash, and that's because we're seeing variability in the elevations of the dunes. So these regional pictures of the coastal erosion hazards allow us to compare vulnerabilities in the different basins. For example, this table here shows the percentage of each stretch of coast that's very likely to experience each type of coastal change during a Category 1 storm. For both areas, most of the coastline will experience dune erosion in the landfall of a Category 1 storm. However, the southeast Atlantic is less likely to experience overwash, and this is simply because the dunes are higher. Now, what's more interesting for the local planner, the resource manager, is the smaller scale spatial variability of the dunes. And this exists over county scales and within single coastal communities. I'll illustrate that a little bit using an example from Hurricane Sandy. This is a forecast that we did as the storm was moving ashore. Again, these are the same color bands representing erosion, overwash, and inundation, and red indicates a high probability of coastal change. The focus here on Fire Island National Seashore. The inner band is the probability of dune erosion. It's very likely for the entire stretch of coast. But what stands out here is this area, that red area with the 98 on it, that indicates in this section of coastline there's a 98% chance you're going to experience overwash. And this is because this area is very low. It's so low, in fact, that there's a 61% chance that it will be inundated or a breach might occur. The photograph in the top left is NOAA's vertical photography after the storm, and this indicates that a breach, in fact, did occur at that location where the yellow arrow is. After the storm, USGS and Corps of Engineers went out to collect data to measure the amount of coastal change. The images on the right are from the same location on Fire Island where the breach occurred, and these are maps of the elevation on the top before Sandy made landfall. This is in May of 2012, and then the middle image is after Sandy made landfall. Orange colors are higher elevations, and you can see in the second image that there's less yellows and oranges. You can also see clearly where the breach cut across the island. The difference between these two images shows the patterns of accretion and erosion. That's the bottom image. The blues are where sand was deposited. You can see about a meter of accretion on the bay side of the island. And that sand came from the front of the island where we saw 3 meters or more of vertical losses of sand. What's important about this image is it shows that vulnerability changes. And this stretch of coastline now, the vulnerability is different than it was before Sandy made landfall. And this is the case for much of the coastline from North Carolina through New York. Before Sandy made landfall, Fire Island, about 20% of the coastline was likely to experience overwash. Now that these elevations have been lowered significantly by the storm, about 70% of this area of coastline is likely to experience overwash in sandy conditions. This illustrates the need to continuously update these models to account for changing beach morphology. In conclusion, a nationally consistent methodology for measuring the coastal change that can be expected or forecasting the coastal change that can be expected during hurricanes will allow planners to identify areas that are more vulnerable than others. The Gulf Coast Report and all of the supporting data are available online to provide information to coastal planners and resource managers as they move forward with plans on how to develop the coastline. And this information can be used in conjunction with the information that Susie and Chris presented. The Southeast and Mid-Atlantic reports will be out shortly. And again, we need to these models can be easily updated with more recent topography, and also as improved models for the hydrodynamic conditions become available, those can also be included. And finally, we're looking for a national method, and we will shortly expand to the West Coast using a very similar framework, but specifically tailored to storms that will occur in the Pacific Ocean. So that is all from me. Thank you.
We have time
Questions?
for questions.
Would the model take into account barrier width?
It
Does it also take into account the elevation across the barrier? I mean, in Texas, we have barriers with beach ridges that represent multiple lines of defense versus one single dune. Other barriers don't have beach ridges. Take into account those?
Right, it does not. What I presented today is looking at the beach system as defined by the most seaward sand dune. And beach width, we have seen that beach width is very important, as is the topography of the dune field behind that initial dune. And that's future work to include those parameters. Mm-hmm.
How important do you think is onshore sediment transport?
Definitely important, but not something we're looking at right now. But it certainly is important during the storms. What we've found is that during the storms, maybe the cross-shore component of sediment transport outweighs what's happening in the longshore. And again, this is something that we are looking at with more focused modeling with hydrodynamic modeling in more focused regions. Yes. Okay. Thank you.
All right. Thank you, Hillary. So we'll move on to our next speaker, Ben Horton, and the title of his presentation is Regional Predictions of Coastal Inundation.
Thank you. These lights. Good afternoon, everybody. Today I'm going to talk about some results at varying stages of completion regarding regional projections of coastal inundations, sea level rise and tropical cyclone activity for the United States and the Atlantic and the Gulf Coast of the United States. I'm giving this talk on behalf of a variety of co-PIs. So this project here comes out of NOAA's services for the coastal zone. The project asked for an integrated work across 4 thematic areas: observations, modelling, Earth system science, and relationship to this particular session, decision support. It was hoped that such a project would provide coastal managers with the tools necessary to better understand how coastal inundation may change through time. So as a group, we were faced with 2 outstanding problems to predict coastal inundation. The first one is regarding sea level rise. We as a community know that there is significant variability or uncertainty with our sea level projections. The IPCC general circulation models are thought to underestimate future sea level rise because of the lack of a full understanding of the dynamic land ice component. And then we also have our semi-empirical model projections, which give a much larger range of sea level for the 21st century, but they lack the physical science basis. So in the aim of our project, we wish to extend the time series of sea level data, including proxy sea level measurements over the last 2,000 years, to better constrain the ocean-climate relationship through known climate deviations such as the Little Ice Age and the medieval climate anomaly. So to do this, we extracted salt marsh sediments from the Atlantic coast of the United States. Now, on the left-hand side of this particular figure, it's important to know that both the Atlantic coast and the Gulf Coast are at the margins or the periphery of the Laurentide ice sheet. This is important because, therefore, those coastlines are experiencing glacio-isostatic subsidence, and for any projection into the future, the spatial variability of this subsidence must be taken into account. Furthermore, the study sites are on the right-hand side that I'm going to briefly go through today. Because of the substance, it creates the accommodation space necessary for the continuous accumulation of salt marsh sediments. So we have results from Florida, North Carolina, New Jersey, and further north into Connecticut. I want to briefly show you one example, and this is the North Carolina study. It was published last year by Andrew Kemp in the Proceedings of the National Academy of Sciences. And to reconstruct sea level in the past, we use foraminifera, which are single-cell protists, and they're very responsive to changes in coastal inundation. We selected 2 sites, Sand Point and Tump Point, and we collected salt marsh material from there and counted the foraminifera. Now, if you're going to understand the past, you must understand the modern. So in the open white squares shown, there are where we understand the modern environment between foraminifera and sea level. We then take 2 cores. We've got cores from Sand Point and Tump Point. We count the foraminifera, and when we've counted the foraminifera, we can use a transfer function or biotic index to reconstruct past sea level. So that's the y-axis taken care of. For the x-axis, to work out timings or rates of change, we use a composite chronology. So we identify plant macrofossils, and we date them through a variety of radiocarbon means: standard radiocarbon, high precision, or bomb spike. We'll use different age markers, be they pollen chronohorizons related to European land clearance, pollution, cesium spikes, and also the standard lead 210. So we have a beautiful composite chronology, and when we use the age model, we can get down to a decadal resolution. So you take the foraminiferal data and you take the age models, and if you put those together, you produce a record of relative sea level changes for the last 2 to 2,500 years. There are 2 important points here. First of all, that we have 2 study sites. They're in differing water bodies in North Carolina, but they produce the same relative sea level record. So we think we have a regional sea level record for the state of North Carolina. We also show a correspondence with the local tide gauge, which gives us great confidence in pushing this record back through time. And the record back through time shows continually rising sea levels. We show a deviation from the linear trend. Sea levels rising from approximately 2.5 meters below present at 0 AD. So we took the same methodology to the north and south of North Carolina. And here are our results. So we show relative sea level records over the last 2 to 2,500 years for Florida, for Connecticut, North Carolina, and New Jersey. Now, these records show great similarities. They all show sea level rising through time, and they all show deviations from a linear trend. But they also show great differences in the rate of sea level rise. So if you concentrate on 0 AD, in Florida, sea levels around -1 meter. If we go to Connecticut, sea levels around minus 1.5 meters or 2 meters. If we go to North Carolina, sea levels around minus 2.5 meters. New Jersey in minus 3.5 meters. Well, what's causing those differing rates of sea level rise is the glacio-isostatic substance from the extinct Laurentide ice sheet. So if we want to distill the ocean-climate relationship, we must remove that rate of glacio-isostatic adjustment. So how we do that is using a database of basal peak sea level index points that are collected over the late Holocene, the last 4,000 years. So what I'm plotting here is the rates of glacio-isostatic substance against the distance from a perceived centre of the Laurentide ice sheet. And we see that the rates of substance increase towards the Delaware or Jersey shoreline and then decrease as you move along the US Atlantic coast towards Florida. So for each one of our study sites, we identify the rates of GIA, and then we can back out this rate from the relative sea level record. So if we return again to North Carolina, on the top diagram we show the relative sea level record of our 2 study sites, the correlation with the tide gauges. Then if we back out GIA, we're left with this sea level record where we can identify 4 periods of sea level change. We have the background in the first millennia where sea level is stable. We then at around 1000 AD sea level rises at somewhere around less than 1 millimetre per year. Then in the last 500 to 600 years, sea level is stable. Before the end of the 19th century, sea level rapidly changes in rate to a rate greater than 2 millimetres per year. Now, as I said earlier, you can then use these rates to better constrain a model that projects the future. So this is a temperature-driven hindcast of the semi-empirical model of Stefan Ramsdorff and Martin Vermeer. So the temperature records to drive the sea level in the past are from Michael Mann's proxy records. And then in the bottom diagram, we show our sea level data in the green with our associated 1 and 2 standard deviation error bars. And then we show the proxy, the reconstruction of sea level from the semi-empirical model in the blue and the green. And you can see for North Carolina that this record, there is a great correspondence between the proxy records and the semi-empirical model hindcast. But the big caveat to this is that there is only one site being used, North Carolina. So the next stage really in this research is to try and get the semi-empirical model to fit the variability that I'm going to show you on the next slide. So on this slide we show the North Carolina record again after we've backed out GIA, and we show New Jersey and Connecticut. Florida is still very much a work in progress, therefore is not shown here. Now we can see 4 major conclusions from this. Sea level has departed from stability in the last 2,000 years. We can see changes that are broadly synchronous over the known climate deviations, the medieval climate anomaly and the Little Ice Age, but their timings differ. So if we look at North Carolina, sea level begins rising at around 1000 AD, whereas in New Jersey that timing has terminated, with Connecticut somewhere in between. All of the records show stability around the Little Ice Age. All of the records show acceleration in the latter part of the 19th century, and in all of the records, the 20th century rate of sea level rise is unprecedented. Now, there are many possible reasons for the variability along the US Atlantic coastline. It could be related to changes in the MOC, but it also could be related to a possible fingerprint associated with the source of melting. So this slide illustrates the fingerprint depending upon the source of melting, be it Alaska, Greenland, or Antarctica. The sea level fingerprint is based upon a premise that if sea level melts, the attraction between the ice sheet and the oceans is reduced, and sea level rise increases in areas geographically distal from that ice sheet. So this may explain some of the variability in the past, but certainly if we're going to have projections of sea level for the US or the Gulf Coast in the future, it must be taken into account, because if you look along the US Atlantic coast, you see a beautiful latitudinal gradient that if we had the melting from these two sources, the rate of sea level rise would be greater in Florida than it is in coastal Maine. The next issue that we had to address was the problems to do with North Atlantic tropical cyclone activity. And this can be summarized in this particular slide, where we have changes in power dissipation, changes in frequency or intensity of hurricanes when the last 20 years of the 20th century is compared with the last 20 years of the 22nd century. And the conclusion you can draw from this is, depending on which model you use, you get a vastly different result. So in our project, we chose the two end members to force our results. We chose the yellow, the GFDL model, or in green, the ECAM model from the Max Planck Institute. So we use those global climate models with an expanded hurricane data set. Now, this expanded hurricane data set uses a large number of synthetic hurricanes. That is because the instrumental or the observational record is just too few, particularly of the extreme high magnitude events, to have a sound statistical basis. So when we do our inundation scenarios, we are looking at regional probabilities of landfall, both under the current climate and also on the IPCC yet to be released AR5 climate conditions. On the bottom graph, we show the 4 AR. So we have a 1 in 100 year event in modern climate conditions, 1 in 100 year event under the ARC 4 AR worst climate conditions, and we can see the differences between those. So as well as looking at the Gulf Coast, we selected 3 areas along the US Atlantic coast to produce our storm surge modelling. So we selected these in combination with our work with the stakeholder groups, but also so they correlate with our sea level data. So we show our records. So one of our areas is in the Northeast, North Carolina, going from Florida up through to South Carolina. So for each synthetic storm, we estimate the storm surge using the slosh model, with inputs to the slosh model provided for each storm. The spacing of our grid cells varies from being around a 0.5 of a kilometre near the coastline, going out to around 7 kilometres in the open coastline. We then couple together our tropical cyclone climatologies with sea level rise. And in this case, we are going to spend a little bit more time using ADCIRC storm surge models. And this, again, is an advent from the stakeholder meetings that we had at the beginning of our project. So we will run, here's our climatologies, we will run future best and worst case scenarios correlated with regional sea level rise. Here we have some of the outputs. Again, this is a 1 in 100 year event without, and a 1 in 100 year with a 1 metre sea level rise. And we get some very interesting nonlinear dynamics. So when we're projecting the reconstructions of the future, we must combine sea level rise and our tropical cyclone climatologies. And this can be nicely illustrated by looking at the present event in New York in contrast to previous landfalling hurricanes. So here we have a time series of around 1800 to 2000. We have the relative sea level records from the battery tide gauges and our proxy salt marshes. And what we can see is if we look at the event of Hurricane Sandy in 2012, it's some 10 to 20 centimetres than the landfalling Hurricane Donna. It's some 30 to 40 centimetres sea level is higher than the historic hurricane of 1893, and it's some 40 to 50 centimetres higher than the historic hurricane of 1821. Now, finally, in the last couple of slides, I'd like to just say that our project also involved, at the beginning of our project, interactions with stakeholder groups. So at the beginning of our project, we set up 3 workshops in North Carolina, Florida, and Woods Hole. And in those workshops, we targeted our invites to representative groups from federal and state agencies, local agencies, businesses, academia, and the NGOs. And that enabled us to basically ask each group, what scientific information would you like from our project to advance your understanding? Now, we had many sort of important aspects from that. They were interested in the temporal scale, so they weren't particularly concerned with our projections of sea level for 2100. They were far more interested in projections at 2030. They also were very interested in different spatial scales to us. As a group of PIs, we were interested in global sea levels, global climatologies, and perhaps downscaling it to the regional level. However, the stakeholders that we met were interested in the local to county and town or the individual lot. And hence we've switched our focus to more of the ADCIRC on selected urban centres. So I could summarise our project with this very simple flow diagram, which we have individual members of our team responsible for individual parts. But perhaps I really should summarise it as follows. Currently, we have obtained sea level data for the last 2,000 years at 4 localities along the US Atlantic coast, and we've begun our tropical cyclone climatologies. The next stage over the next 12 months is to include the variability that we see in sea level in our sea level modelling, combine it with our tropical cyclone and surge modelling to give us the future regional inundations for the US Atlantic and Gulf Coast. We've built up good relationships with our stakeholders, so therefore we're hopeful that we will achieve information transfer. Thank you very much.
Take one quick question. Susan.
What are you actually doing to get the information back to the stakeholders? It's pretty well known in the social sciences that look at this particular relationship between the science and the decision makers, that sort of just handing over the report or the maps or the database is not particularly useful. So I'm wondering, what are you doing to help that?
Well, I think that your point is very well met, and that's why we wanted to meet them at the start of the whole process, because and from that's how we've, our original plan was to produce sea level and tropical cyclone climatologies at 2100. We were interested in using the slosh model across the whole of the coastline, and then from those stakeholders they said, well, we're not interested in 2001. We want to know what 2030 is, so we're focusing our efforts on that particular time slot. And then they were interested on the smaller spatial scale, so we're again focusing using ADCIRC on particular urban areas. Now, the aim is to return to the same stakeholder groups, maintain the relationship with them. And we put a lot of effort into those workshops. And we have a PI who's particularly responsible for that particular element.
Okay, thanks.
Thank you.
Thank you. We'll move on to the next presentation now, and it'll be given by Ning Lin, and the co-author is Carrie Emanuel. Title is Storm Surge Simulation and Ensemble Forecast for Hurricane Irene.
Hello, everyone. So we were going to talk about Hurricane Irene, but here comes Sandy, so we changed our title to Storm Surge Forecasting for New York City. So we're going to talk about preliminary results for Sandy in addition to Irene. So we have been doing a lot of long-term risk analysis for storm surge for New York City using various models, including slush and ADCIRC with various grid resolutions to conduct large number of synthetic storm simulations. These models, meshes, and the method we use to increase the computational efficiency can also be applied to real-time forecasting, where a large number of ensemble forecasting may need to be run quickly. Also, to reduce the computational time, we use parametric modeling of wind and pressure fields. We first model the gradient wind field using an analytical profile developed by Emanuel and Rotono. The red curve on the plot is this profile, compared with some other widely used profiles. And then we translate this gradient wind to the surface level with a wind reduction factor accounting for the inflow angle and add the estimated background wind to account for the asymmetry of the wind field. Since surge is highly sensitive to the wind field, we also conducted sensitivity analysis for these parameters. For example, we compared these different wind profiles to find that Emmanuel Rotono gives us the best estimation of the surge statistically. We used the simple Holland model to estimate the pressure fields. So we're going to talk about two cases, Hurricane Sandy of 2012 and Hurricane Irene in 2011. So first, Sandy. This is a handcast of the surge from Sandy. We carry out the simulation for 100 hours before and during landfall using the BDEC or best track data of the storm parameters, including storm track, intensity, and size. As example, here we are showing just the numbers for this, the values of these parameters when the storm was at its closest point to the battery in New York City, including the maximum wind speed, central pressure, radius of maximum wind, forward speed, and the distance to the battery. So using these parameters over time, we use the parametric models to simulate the wind and pressure fields to drive the storm surge simulation using ATHIC model with resolution about 100 meters around New York City. Such a simulation takes about 1 minute using 8 processors. So this storm moved almost perpendicular to the Jersey Shore and made landfall southwest of Atlantic City with its counterclockwise wind pushing water into New York Harbor and generated high surges around New York City. So with a surge about 3.25 meters at battery. So we carry out real-time forecasting using the HWolf and the GFDL model predicted storm parameters at 78, 54, and 30 hours before landfall. This slide shows the results for HWolf forecasts. So HWolf model predicted tracks were off for at 78 and 54 hours before landfall, the tracks were to the north of New York City. But they did a very good job at 30 hours before landfall in terms of predicting both the track, intensity, radius of maximum wind, and other parameters. So the surge predicted by HWolf simulation was close to the results from the BDEC simulation. This slide shows the results from GFDL forecasts. So GFDL did pretty well in terms of forecasting the tracks, especially early on. At 78 and 54 hours, the track was very well predicted, and but the wind speed was a little underestimated, so the surge was underestimated compared to the BDEC simulation. But at 30 hours, GFDL's prediction was actually less accurate. So to sort out why, we carry out sensitivity analysis. Here, the first plot is the original GFDL prediction, and this is we use the BDEC pressure and with other parameters unchanged, and the surge was increased to 1.45 meters. And this is we use the BDEC the maximum wind speed, and with other parameters unchanged, the surge was increased to 1.7. I can't see it. And then this is using the BDEC track, but with other parameters unchanged. Surge was 2.27, and this is using BDEC radius of maximum wind, and with other parameters unchanged, the surge was 1.92. So getting any of these parameters right can get us to the right surge. Because surge is highly sensitive to all of these parameters. In other words, we cannot use any one of these parameters, such as maximum wind speed, to predict the surge potential. So how about the observation? How can we compare with observation? Actually, the surge shown in the green was about 2.75 meter at battery. So actually, using the BDEC data using parametric method we showed overestimate the surge by about 0.5 meters. So we think one of the main reasons is because Sandy was not a typical hurricane. It was a hybrid storm undergoing extensive extratropical transition. And with very asymmetric wind fields. So using simple parametric model may cause overestimation of the surge. So now we're trying to use weather research and forecasting model to generate high-resolution wind pressure fields to drive the surge. In real-time cases, for such cases, we still can use the simple parametric method as a filter to sort out which are the important ensembles that may cause high impact or have high probabilities, and then use high-resolution WRF simulations to carry out more accurate simulation. And sometimes the simple parametric model works well, such as for Irene. So this is a hindcast using the BDEC or best track data of the surge. So this storm moved to the right of Battery with relatively low intensity. So the surge was 1.3 meters at Battery. And the surge was, again, also right at high tide. So the water level was about 2.1 meters. This plot shows that our simulated water level compared very closely with observed water level. So because Irene is more typical hurricane. We also carry out ensemble forecasting for Irene using our long-term surge risk analysis method. So for this method, we use a simple hurricane model to generate a very large number of ensembles given the storm environmental conditions. We first generate the storm genesis using a random seeding technique, and the storms are moved according to the wind with a beta draft correction. And then along each generated track, we use a deterministic ocean-atmosphere coupled hurricane model to estimate intensity. And then we found the storms that are affecting the region of interest and conduct storm surge simulations. So in this case, we use 50 ensembles of the storm environmental conditions predicted by the European weather forecasting model to generate 1,000 storms 3 days before it passed by New York City on the left, and another 1,000 storms 2 days before it passed by New York City to the right. And here are the histograms of the surges generated by the two hydrodynamic models. So Irene's surge, about 1.3 meters, was at the middle to the high range of this probability charts. And it had 9% to 10% probability to be exceeded, according to this ensemble forecasting. And the highest surge level from the 3 days before was about 2.3 meters, and the highest level from 2 days before was about 2.1 meters. So here we're comparing Irene with the worst case predicted 2 days before. So this worst case storm to the right moved to the left of Battery with higher intensity and with its very strong counterclockwise wind pushing water into Lower Manhattan. So the surge was 2.1 meters. So if this happened at high tide, the water level would approach 3 meters, which would inundate much of low-lying area in New York City. That we have seen from Hurricane Sandy. So in summary, the real-time storm surge forecasting have been performed for New York City using our methods. We used a simple parametric hurricane models to speed up the simulations. It worked very well for Irene, but overestimates the surge for Sandy. So we're trying to use other methods to check that. Large numbers of ensemble surge forecasting can be conducted effectively and efficiently for hurricanes for this area, as we have developed very efficient methods to generate storms and the storm surge in real time. Thank you.
Time for questions. Okay, the next talk, how sea level rise and storm climate impact the looming morpho-economic bubble in coastal property values, going to be given by Dylan McNamara.
Okay, so a very traditional start to an AGU talk with this image here. This is the... Sorry. That's all right. Just going to play. Okay, cool. So now you guys know what I'm going to say. You saw my notes on there. So this is the sock puppet from the now extinct company Pets.com. Pets.com is sort of the flagship company for the bursting of the dot-com bubble in the early 21st century. They went from their first appearance on the NASDAQ to complete liquidation in 268 days. When they first appeared on the NASDAQ, they had only existed for a year, and they had generated about $600,000 in revenue, yet they had spent $11 million on advertising. So not surprisingly, Pets.com no longer exists. Their bubble burst. So to give sort of a semi-formal definition of a bubble is when, an economic bubble is when the value of an asset is inflated relative to its fundamental value. So with regard to Pets.com, when they first popped onto the NASDAQ, they were trading at $14 a share, even though they were losing millions of dollars every month. So clearly that was a bubble. Another bubble that is very recent and may have impacted some people here in the audience is the bursting of the housing bubble. And again, that was a case where the value of homes across the country became significantly inflated relative to their fundamental value. So here I've overlain on top of that home a picture of a town. This is Ocean City off the coast of Maryland. And what I'm going to talk about today is the possibility that towns like this, towns that are sitting on top of barrier islands up and down the East Coast, New Jersey, North Carolina, off the coast of Maryland, have the potential to be a bubble that will burst. More specifically, what I'm going to talk about is the role that increasing rates of sea level rise and storm climates play in altering the manifestation of this bubble and its potential for bursting. Now, I think when we think about this system, we all sort of have a qualitative feeling for how the dynamics play out on human-occupied coastlines. But if we're going to make some headway in contributing to anticipating one of these bubbles occurring and informing policy, we need to have a quantitative understanding of these dynamics. So what I'm actually going to talk about today are two numerical models that I've created with my colleagues to investigate how sea level rise and storm climate impact this looming bubble in coastal property value. Now, notice here I'm calling it a morpho-economic bubble. So unlike the bubbles that I talked about to start, this is one that is not just an economic bubble. It depends also on the coastal morphology. And that is because human-occupied coastlines are a tightly coupled dynamical system. Natural coastal dynamics are coupled to economic dynamics. So if there is a bubble in property value, it is necessarily a function of both the economics and the morphology. So the two models I'm going to talk about today are, they sort of are in two different camps in terms of their approaches to how you understand the system. In the first case, I'm going to describe a dynamic model. So as the word suggests, that's a model whereby you evolve the variables over time, and you look at how the system evolves through time. The more traditional approach to modeling these kinds of coupled systems, at least in resource economics, is to do something called a constrained optimization. And that is what I'm referring to as an equilibrium model, because in that case, you are putting all the necessary ingredients into the model and then looking at the system when it's in equilibrium and then investigating some of those characteristics while it's in that state. Okay, so I'm going to describe how both of these models work to simulate all of the coupled dynamics, both the physical coastal dynamics and the coastal economics. Okay, so in terms of the physical dynamics, in the dynamic model, I'm using a node-based barrier island model. So here we have nodes, those white nodes there located in three-dimensional space that change their positions through time and exchange sediment within this simplified representation of a barrier island. And not only do they exchange sediment with the barrier island configuration, they have the capability of exchanging sediment with offshore sand sources and sediment that's inside of a coastal inlet. And I don't have time to go into all the details, but suffice to say, it sort of simulates the dynamics that you see listed there. And the model, is well vetted in the literature. It does a pretty reasonable job of reproducing observed barrier island behaviors. In the equilibrium case, this is a much more stylized approach, an analytic approach to simulating the system. Here we have what an economist would refer to as a state equation that shows how the coastline position evolves through time. And in this representation, we have three ingredients for dynamics that alter the coastline position. One is erosion from sea level rise. So that's just put in as a linear reduction in the coastline position. We also have an exponential relaxation of the shore face. So in the case that nourishment occurs, beach nourishment, and the shore face profile steepens, it will relax back to its equilibrium profile at just some exponential rate. And then more recently what we've done is to add in storms in the following way. Storms come and have the capability of removing the entire nourished profile. So to the extent that nourishment has occurred, if a storm hits, it will remove all of the nourished sand. Okay, so with respect to the economic dynamics that we simulate in these models, in the dynamic modeling approach, here we have what is called an agent-based model. And so we have heterogeneous agents whose primary goal is to maximize profit. You can look at those faces and realize that they're going to maximize profit. Even if it means suffering for all of society, they will maximize profit. The decisions that they're making are whether or not they're going to make bids on coastal property. And the things that they weigh in considering making a bid on coastal property are the benefits and costs of owning that property. So, for example, they weigh the income that they would derive from the coastal property, the return that they would get as a comparison on other safe investments, and then the costs associated with their expectations of future damage. And then they also are considering the costs to mitigate. So they know that they're going to have to nourish the beach. They may or may not have to nourish the beach and build the dunes. And they calculate those costs as well. What's novel about this particular model is that the way that the agents generate their expectations for future change in the system are that they have the capability of looking into the past in the model and seeing how the environment has been evolving. But they also have the capability of running the model that they themselves exist in forward in time to sort of extrapolate into the future how the system is going to evolve. So they wrap all these considerations up and come up with a bid on coastal property. And those with the highest bid are the ones that become property owners at any given moment in time in the simulation. And then those property owners have a referendum to decide on what their nourishment procedure is going to be, and that's based on their expectations that they've developed. So out of the model comes things like nourishment behavior and property value. Now the equilibrium approach is quite different. Again, it's an analytic approach where, without going into the details, it's a constrained optimization. So the constraint equation is that state equation for the beach position that I showed before. And the optimization that is performed is to optimize total net benefits. So again, it's just considering benefits against costs. And they're choosing, so the optimization comes in the form of them trying to find out the nourishment interval in time that will give them the maximum net benefits in the system. And so these functions, the benefits and costs, right? Benefits are associated with amenities, the fact that you have a wide beach in front of your property. Costs are associated with, nourishment sand, going out and getting the sand and dredging it and putting it onto the beach. So they are intimately tied to the constraint. They're a function of the constraint, X, and they're also a function of economic parameters, things like discount rates and costs of sediment. Now these functions, F and G, that connect the constraint to the benefits and costs is something, part of the utility of this approach is that those relationships are well rooted. They have a strong foundation in the empirical data. So you put all those things in there, and what pops out of this analysis is you can solve to find the optimal nourishment interval. And then once you do, you immediately can go back and calculate the total net benefits. And this is done all the way out through infinite time. And so once you've done that, you actually get the realized property value at that moment, discounted all the way through the future. Okay, so first I'm going to show some results from each of the approaches that sort of are characteristic of the approach themselves. In the case of the dynamic model, of course, you get these time series. You get a time series for, I'm showing property value, dune height, and beach width. And so with the property value, what you see there is that the property value starts off relatively high, and then you see the indication of damage events. So that's when you have like a sandy situation, and it damages the coastal properties. Notice they quickly rebuild, and reestablish the system. But over a long period of time, eventually, all of the agents in the model abandon the coastal property. So that means there's no economic incentive in the system any longer for them to purchase coastal property. So that's marked by the white X. And underneath that, in terms of their mitigation behavior, you can see that they ramped up their mitigation as their world got more and more precarious. They increased their height of the dunes and they increased the frequency in which they were nourishing. But in any case, all of those mitigations eventually led to abandonment at the end of this simulation. In the equilibrium model, you don't get these sort of time series pictures. You get what is going on in the optimum state. So in the right-hand side top plot, so both of these plots are parameter space plots for, on the vertical axis is storminess, and on the horizontal axis is erosion from sea level rise. So what you can see contoured in the top plot is the nourishment interval, the optimum nourishment interval. And so yellow is longer time, 18 years, and red is shorter nourishment intervals, so more frequent nourishment. And so what you see as you move from left to right on that image is that as the erosion from sea level rise increases, they do nourish more frequently, and that sort of makes sense. As you increase the storminess, they actually nourish less frequently, which is kind of interesting. They are basically, economically, what's happening is that they're deciding, rather than take the risk of nourishing and having a storm come and take away that nourishment investment, they're getting around that by nourishing less frequently. That's the optimum response in that case. On the bottom below that is property value. So that's contours of property value. Yellow is high property value, red is low property value. And that one makes very intuitive sense. The more erosion there is from sea level rise and the more storms there are, the less the property value. Okay, so both are giving you indications of property value and nourishment behavior. Where the models are similar, and the extent that I'm going to talk about a bubble, is that along the East Coast there have, historically, the government has subsidized nourishment costs at a rate of about 66%. So the government has actually paid 66% of the cost to nourish these beaches. And as we've seen in those results that I just described, nourishment is clearly an intrinsic part of the property value. So it begs the question, what happens if this subsidy were to disappear? Do property values all of a sudden, are they considerably inflated relative to their fundamental value? Are they a bubble? Well, in the dynamic model, yes. So here I'm plotting on the vertical axis the fractional reduction in property value if they were to lose the subsidy to nourish as a function of sea level rise on the horizontal axis for two different storm climates, one that's comparable to what you'd find in New Jersey and one that's comparable to what you'd find in North Carolina. And what you can see is that in worst case scenarios, high rates of sea level rise, upwards of 10 millimeters per year, you can get a reduction in property value of nearly 40% just from the government removing the nourishment subsidy. So that wouldn't happen instantaneously. It would take some time to unwind that position, but the value of property, all of a sudden, if that decision gets made, would be inflated relative to its fundamental value. The equilibrium model suggests similar magnitudes of reduction. So again, that's the exact same plot, fractional reduction in property value. And in this case, in the horizontal axis, erosion from sea level rise. And here, again, you get a significant reduction in property value. Interestingly, storms do change the amount of reduction in property value in this model. And that's because, as we saw before, the nourishment behavior is intimately related to how often storms occur. Unlike in the dynamic model, they're primarily nourishing just as a response to fight erosion from sea level rise. Okay. So in the dynamic model, one of the useful things about the dynamic model is that you're watching things play out through time. Can you learn anything as you head towards this scenario of abandonment? For example, one question is, how does the loss of subsidy, the government subsidy for nourish, how does that even compare to sea level rise and changing the amount of time that it occurs until abandonment? And another question is, are there any precursor signals in some of the variables in the dynamic model that suggest to you that abandonment is right around the corner? Well, with respect to the first question, here is a contour plot showing sea level rise on the vertical axis and an amount of nourishment subsidy on the horizontal axis, and the contours are the amount of time until abandonment occurs in the simulation. And what you see is that increasing rate of sea level rise shortens time to abandonment, and a decreasing nourishment subsidy also shortens time to abandonment. They don't have the same impact, but similar. So losing the subsidy to nourish is just like having an increased rate of sea level rise when it comes to shortening the time to abandonment. Now, what you see oftentimes in stock markets before a bubble crash is a dramatic increase in what they call volatility. So high volume trading, lots of trading, and dramatic swings in prices. So in the dynamic model, you actually see similar things right before abandonment occurs. This is a plot of the volatility of property value in those simulations as a function of the number of years before abandonment for two different scenarios for sea level rise. So here on this plot, at 0 is when abandonment is occurring. So what you can see is that right before abandonment, in the number of years before abandonment occurs, there is an increase, a significant increase in property value volatility as properties are changing hands and agents are jumping in and out of the market because of how precarious the system has become. Very much like what would happen in a stock market bubble right before it crashes. So I'm a little bit over, so I'll leave the conclusions up and entertain any questions. So I can describe the effect of the insurance subsidy in that, so what's not in the model is something that economists call risk aversion. I don't have risk aversion in there, but you can simulate, when the agents make those calculations for costs, you can increase their cost calculation in the same way that you'd have to increase insurance premiums. And if you do things like that, it does exactly what you'd expect. It causes a delay until abandonment occurs, and people rebuild quicker after storms. But what we have not put in his future work is to put in what's called risk aversion.
Are you talking to the Corps of Engineers about this?
No.
You should, because they're thinking very much about reducing the federal subsidy.
Yeah, I mean, I hope they would see what impact I'm suggesting it would have. I'm not necessarily going to tell them what they should or shouldn't do, but it will have, all indications are that it's going to have a dramatic impact on property value.
Okay, and we'll move on to our final presentation by John Anderson. The title is Unprecedented Coastal Response to Global Change, a Case Study of the Upper Texas Coast.
This is the, okay, where's the button? There it is. Well, I can't see the screen anyway, so. All right. Okay, well, thanks for sticking around. I think with, I'll just move right on to the first button. Okay, we've heard talk today about the acceleration of sea level rise. This is a curve for the Gulf of Mexico that was originally put together by Tor Tornquist at Tulane, and then we added to this data. And it shows the acceleration of sea level rise that's taken place in historical time. And I think the question we want to get at is, what's been the impact of this sea level rise? But I think there's other factors that need to be taken into account. And one is that if we look at the rate of hurricane impacts in the Gulf of Mexico, we look at the long-term rate over thousands of years from paleo records, the indication is that, at least for South Texas, the probability of landfall is about 0.4% annual landfall probability for that area. Since 1900, the Upper Texas coast has experienced direct impacts from Category 3, 4, and 5 storms at about a 6.4% probability. Now, whether that's a statistically viable comparison or not, I'm not here to say, but the point is that clearly the rate of impacts has increased in historical time. So we've seen an unprecedented rate of sea level rise, and we've seen what appears to be an unprecedented rate of storm frequency, and again, the emphasis on unprecedented. As far as sea level rise is concerned, if we take the current rate of rise, I should have pointed out in that curve earlier, which is about a little over 2 millimeters per year in the Gulf of Mexico, and the long-term rate of rise, which is about 0.5 millimeter to 0.4 millimeters per year. We're talking about roughly a 5-fold increase in the rate of sea level rise, as Ben Horton pointed out, in historical time over the last few centuries. So about a 5-fold increase in sea level rise and a significant increase in storm impact. Now the next question is, has this manifested itself on the at the coast? This figure shows a figure from the Bureau of Economic Geology, who have done a really nice job over the last several decades in keeping pace with rates of shoreline migration. Texas has one of the longest records, in fact, of this sort, because aerial photographs go back actually to the early 30s. And as you can see, let's see if I can get the pointer going here. I don't guess so. Okay, well, can't get the pointer going, but as you can see, for Galveston Island, which is in the middle of the slide, the average rates are on the order of about 1.5 meters. This is in feet per year, by the way, which is the way they exhibit the data. About 1.5 meters per year for Bolivar Peninsula, which is on the upper right, about the same rate. And there are variations in that, which are mainly due to anthropogenic effects, the construction of the Galveston seawall and other anthropogenic effects. Now, the important thing here is if we take the history of the barrier that we know pretty well. In fact, we probably know more about Galveston Island's evolution than any other barrier island on Earth. It's certainly been studied longer than any other barrier island on Earth. And so lots of drill cores, lots of radiocarbon dates. And we know that the island had a history of growth from about 5,500 years ago right up until about 1,200 years ago. And at that point, then, the trend reversed itself and the island began retreating as it exhausted its sand supply. Now, that solid red line on the right just simply takes the equilibrium profile and sort of looks at what the rate of erosion, if we take the current day rate of erosion, how that compares to the actual erosion rate that we see over long periods of time. And the point of this slide is to say that if we take the current erosion rate of 1.5 meters per year or 1.5 kilometers per 1,000 years, had this rate been occurring over the last 1,200 years, the barrier would have actually shifted landward considerably further than it is today. In fact, the next little barrier to the west of Galveston Island, Follett's Island, is migrating at a rate of 3 to 4 meters per year landward. And so we take that rate, Follett's Island would not even exist today. It would be completely gone by now. So that's certainly a pretty strong indication that these rates that we're measuring today are unprecedented. Now, if we also take the amount of erosion that's taken place over historical time, we can calculate the volume of sand loss. And the historical sand loss for Galveston Island comes out to be a little over 200,000 cubic meters per year, again, using that measured rate. And so that sort of just gives us a ballpark number that we can now look at and see how that compares to the long-term rate. And these photographs just show good evidence of the fact that the beach profile is, of course, changing. The photograph at the top showing a seawall where the elevation has been lowered, the beach elevation has been lowered by a little over 1 meter since the seawall was constructed, in this case back in the 60s. And the photograph at the bottom is taken right after Hurricane Ike, just to point out that a lot of this readjustment of that equilibrium profile, of course, takes place after storms, and there's some reequilibration after the storm, but for the most part, these beaches are left with pretty low profile after these storms. Now, there have been attempts in the past so the question we want to get at is, using the sand budget, how much erosion is actually occurring today, and again, how does that compare to the long-term rate? And the slide in the bottom left here shows a couple of different attempts at getting at the sand budget for Galveston Island. The large orange arrows are an attempt by the U.S. Corps of Engineers to come up with a sand budget. The green numbers are the Corps of Engineers numbers. The red numbers are ours. The differences there are first in sort of underestimating anthropogenic effects. And for example, where the large red arrow is there, and it says 243,000 cubic meters of sand, the budget for sand transport, that actually assumes that the amount of sand that's being trapped by the jetties reflects the longshore transport of sand. But that does not take into account what's shown on the bottom right here, which is a historical map of this inlet that shows a large tidal delta, ebb tidal delta, that was located offshore prior to the time the jetties were built for the Houston Ship Channel. And what's happened is that a lot of that sand's been eroded, moved onshore, and accreted to the beach. So you got to subtract that from that longshore transport. That's not really part of the longshore transport scheme. So that's why the numbers are different. So we need to get a careful budget if we're going to ultimately say, well, what's the current rate of retreat again, and how does that compare to the long-term rate? That really involves getting at a good sand budget. And we can, first of all, keep in mind that there's virtually no fluvial input of sand, no fluvial input of sand to this system today. So we don't worry about much new sand coming in. In fact, the Galveston seawall and the jetties that are constructed off the seawall are trapping very little sand. Those beaches are being nourished today. Most of the sand that's eroding from the island goes to potentially three places. One is overwash into the backside of the barrier, into West Bay. The other is offshore storm transport. And then the third is a tidal delta that's located at the western end of the island that's shown here in the lower left-hand slide, which is a very prominent feature. It's actually one of the few natural tidal deltas anywhere on the Gulf Coast, which is one of the reasons why Galveston Island's an ideal place to do this sort of analysis. And so what we've done is to try to calculate the volumes of sand in these different areas, and then we're using the ages, radiocarbon ages, try to get at the flux. Now for the red dots here show the locations where we have cores in the back barrier environments where we have radiocarbon dates. And for all practical purposes, overwash is insignificant on Galveston Island, and that's largely because the barrier is quite wide and it's quite high. Offshore flux, on the other hand, if we take the cores we've collected offshore and done radiocarbon ages, we can just sum the normal number of storm beds, which are shown in yellow here, over a period of a few thousand years, and we can come up with a volume for the offshore flux. And our estimate based on that is in the range of about 900 or so thousand cubic meters, or 900 cubic meters per year. So now we've got a backshore flux and offshore flux. The third place we have to get at is the tidal delta. How fast is the tidal delta growing today versus in the past? So the red dots again show cores, and for a number of these cores we have radiocarbon ages. The ages extend back for the modern delta to about 2,100 years, suggesting that the delta has been around the modern delta has been around for that period of time. If we take those cores and we calculate then the flux into the delta over that 2,100 year period, it comes out to about 4,300 cubic meters per year, roughly 4 times greater than the offshore flux due to storms. Now let's look at the more recent fluxes. And in the case of San Luis Pass, we've done that, or the inlet, I should say, we've done that using both sediment cores, where we have radiocarbon ages, and reconstructing the migration of the inlet and the delta. And that information shown here. And it suggests that over the long term, that the inlet has migrated at a rate of about 2.9 meters per year. That's just observing using your sediment cores how the inlet and the associated delta has migrated. If we compare that to historical charts, we come up with a migration history over the last 200 years of about 7.5 meters per year, which is more than twice the long-term rate of inlet migration. So based on this result, the historical sediment flux to the tidal delta has been about 10,000 cubic meters compared to a time average flux of about 4,300 meters over millennial time scales, and also the rate of migration of the inlet has more than doubled. So from that, our estimate of long-term sand fluxes from the shore face of Galveston Island are significantly less than what we would calculate if we just take the current rate of erosion and we calculate that volume over time and how much sand would be lost. And that volume would be significantly greater over the long term of what we're actually observing, which is telling us that the current rate must be unprecedented. Additionally, the growth of San Luis Pass flood tidal delta and the migration rates of the San Luis Pass delta have more than doubled over geological time relative to historical time. Erosion rates have more than doubled from geologic time to, for Galveston Island, therefore, or at least that's our conclusion. So we think we do see evidence here that there's an unprecedented rate of change, and we think we can document that, and I think this is what we need to do when we're talking to stakeholders. Certainly in Texas we need to do it, because people really haven't accepted the fact yet that the rates, or that what they're observing is an accelerated trend. Now the response to this, which was really brought about by Hurricane Ike, which did, of course, devastated Bolivar Peninsula and did significant damage to Galveston Island, is what's called the Ike Dike, which is a very serious proposal to build a dike. The yellow here is the current Galveston seawall. The red is the proposed dike, which would be an extension of that seawall, and then a set of locks, very similar to the Dutch situation, that would occur both at the mouth of Bolivar Peninsula and at the mouth of that natural tidal inlet. So that'd be the end of our natural tidal inlet. So this is the proposed solution to the problem. It's a hard solution. It's tens of billions of dollars. And as recently as 2 weeks ago, the city of Galveston approved a $250,000 feasibility study to look into this. I think the other thing I wanted to emphasize is that, and I've seen this model shown more than once, that as scientists we need to emphasize to the public that, first of all, current rates of change are unprecedented, and the more evidence we have for these sorts of things, I think the better. I think the other thing we need to point out is that sea level acceleration, sea level rise is happening, as Ben pointed out. It's not something we're predicting using IPCC models. It's going to happen 100 years from now. It's something that's happening now, and the impacts of that accelerated sea level rise in conjunction with increased storm frequency is having a significant impact on our coast. And the other thing is that these inundation models, where we simply take the landscape and raise sea level and flood the landscape, are, in my opinion, greatly underestimating the impact of sea level rise. The figure on the bottom right there shows what the shoreline, offshore Texas, East Texas, has done over the last 7,000 years. The dotted lines show the shorelines. And just point out that and that green splotch to the right where you see the number 15 meters per year, that's the average rate of erosion at that period of time. When this is back when sea level was rising about 5 millimeters per year. At that time, when that rapid retreat was taking place along the East Texas, western Louisiana shoreline, Galveston Island was forming. And we see this all up and down the Texas coast. So I think the response to accelerated sea level rise is far more complicated than simply raising sea level and seeing how much land is inundated when we're talking about barrier shorelines. Thank you.
Questions, John?
How much marginal variation do you see in that erosion rate? So you keep one erosion rate, but does that kind of relatively uniform along the barrier island, or do you see substantial variation along the barrier island?
Are you talking about modern or long term? Yeah. Well, actually, we see substantial variation in both. If we look at the modern erosion rates, they vary from stable, and in central Texas, there's not only stable, but actually growth in some locations, to areas like East Texas and South Texas, where the rates are on the order of about 3 to 4 meters per year of landward retreat, and about that same order of magnitude over the long term.
So the rate you use in an average, spatial average?
Well, I think we have to look at each barrier individually, because the reason for that variability is sand supply. And the sand's not coming from the rivers. The river supply of sand to the Texas coast was cut off thousands of years ago when the rivers were flooded to make bays like Galveston Bay. The sand that's coming onto the coast here in Texas, and I suspect this is true for a lot of the coasts of the world, is sand that's being ravined offshore. So it's the very process of sea level rise and shoreline translation that's producing the sand that's nourishing the beaches. So if that transgressive surface is ravining an old fluvial channel, it's adding sand to the system. If it's ravining mud, it's not adding sand. So we take that long strike variability, and we've demonstrated this some years ago, that's largely related to the variability in the sources, the offshore sand sources that are being ravined or being mined as sea level's rising. You're talking about in the tidal delta. I'm sorry, are you talking about the Corps of Engineers? Yeah. I'm sorry, I didn't make that clear. That's if you take the current rate of retreat and you assume the profile is an equilibrium profile, then over a period of time you can take that amount of sand that's actually been removed over some predictable, over some distance to come up with that volume. And what we did here was we took the average rate of retreat, which is to the west of the seawall, which is about 1.5 meters per year, and we took that over, several centuries, and then we just calculated that volume from that number. So it just sort of gives us a number that it's a number that we can work with, tells us, when we're doing a sand budget, theoretically, that's the number we ought to come up with in the end, but we're falling way short of that, and what the message there is, then that implies that current erosion rate that we're using to get that number must be faster than it has been over the long term.
Okay, that concludes the session. I'd like to thank all the speakers again and remind you that we have a poster session tomorrow morning. Thank you.